Alrighty, guys. Good afternoon. All right, so what we're going to look at is a transformation formula using function notation. And we're using function notation because this formula can transfer to any parent function and it does the same thing. So we're going to learn how it affects each one throughout the year. The first one we're tackling is the absolute value function, which is why I wanted to start with that one and then show you the movements one at a time. And here we're still going to do one transformation at a time, except we're going to see it across different parent functions. All right, so first thing I want to do is go over this transformation formula. All right, so from left to right. So we have f of x, and f of x is the same thing as y equals. All right, and the function part is a function of x. That's what the f means. And like I just said, it applies to all the parent functions there. All right, and we're kind of going to go through this formula from left to right. So f of x, same thing as y. And then we have plus or minus. Plus doesn't really do anything for us, but sometimes it's a minus, and minus tells us something. And if it is a negative, a minus, a negative in there, that is going to be a reflection about the x-axis. All right. Then we have the a value. All right. Now, to be clear, the negative or the plus has no effect on what a does. So we're going to leave those plus or minus out of it, okay, and look at just the number that a is, the absolute value of a. So if a is a negative 5 or a negative 0.5, the negative part doesn't matter. The negative tells us it's a reflection about the x-axis. That's all we need. Now, as far as just the a number, the absolute value of that a number, okay, is going to tell us something. So we have two things that it can tell us. All right, so first of all, the A is a dilation. And we've seen dilations in geometry. That's where shapes were bigger and smaller based on a scale factor. And it's very similar here. But what we have is something called vertical stretch and vertical compression. So the vertical stretch, I'll put VS for short sometimes, is when your A value is bigger than 1. Okay, so it's not equal to 1 because if it was 1, there's no change. Anything times 1 is itself. So if it's a number bigger than 1, like a 5, it's gonna blow up by a factor of 5 times whatever. All right, so vertical stretch by a factor of A. All right, and then the second thing is a vertical compression. All right, and I'll put VC sometimes. All right, now this one's very specific. It's between 0 and 1, okay? So we know why it can't be 1, but it can't be 0 because anything times 0 is just 0, just kind of wipes it out. All right, but any decimal or fraction between 0 and 1 is a vertical compression, okay? Again, the sign has nothing to do with it. So if I have something like an a value as a negative 3, okay, negative 3 isn't between 0 and 1 either. Negative 3 means that it's been reflected, and that 3, since it's bigger than 1, is a vertical stretch. But like I said earlier, if we have 0.5, 0.5 is between 0 and 1, that is a vertical compression. Okay, even if it was negative 0.5, forget the negative, 0.5 is a vertical compression because it's between 0 and 1. So I want to make that very, very, very clear. All right, so that's a common thing students get mixed up on. Another one is your H value. All right, now we'll get more into detail in the examples about H, but basically H is just a translation, a horizontal translation. Okay, horizontal goes from left to right, so something like this. Okay, now if H is a negative, H will move to the left. If H is positive, it will move to the right. All right, use my magic pen tools. I'm going to make this smaller so it fits. I suggest everybody get a magic pen. Bam. All right. Okay, now K value. Okay, it's also a translation, but a vertical translation. Okay, don't get translation mixed up with transformation. Transformation is all of these. Translation is just one part of a transformation. just to kind of show you that. All right, so up and down, right? Okay, so again, if k is negative, it will move down. And if k is a positive, plus sign, it will move up. All right, simply stated. So there are transformations, and they can tell all that from the formula and from the equations of whatever parent function we're looking at. All right, so here's some exercises or some examples. Name the parent functions, describe the transformation effect, and write the equation of the graph. So we'll do those things based on given information from different things they give us. So we can base it off like either the transformation or the graph or the equation, and we'll kind of interchange them. All right, so let's look at this first graph here. All right, so first of all, we need to recognize what it is. It's a V shape, and the only parent function I know that has a V shape is the absolute value function. And that starts at the origin, goes up this way. Not a very straight drawer, but there it is, okay? And that is y equals the absolute value of x. All right, so those things that we tested on the last week, that's why we wanted you to kind of memorize those so you could recognize them parent functions. All right, so with that being said, we know the name of this. This one's absolute value. Okay, so the blue is what's been transformed, so which means it moved to the left 2 units. You can just simply count them, 1, 2. All right, so we're going to write the effects. I'm going to put translates 2 units left. There's the effect. Then we're going to write the equation. All right, so with this equation, it's good to know that that's our parent function, and this is our transformation formula, plus minus a. And what I'm going to do is I'm going to fix this transformation formula to fit absolute value. So in essence, what I'm going to do is basically these parentheses takes on whatever parent function we are looking at. So since absolute value has the bars, I'm going to replace those parentheses with the absolute value bars. Just like that. There it is. And you see how very similar they look. All right. Okay, so since the only thing that happens to this function is that it moves to the left, we're just worried about this h right there. So here's how it's going to go. So we're going to write the equation, f of x equals, so it didn't open downward, so there was no reflection, so we're going to use the plus, we don't need to write plus. There's no dilation, so it's a 1, we don't need the 1, anything times 1 is itself. So basically what we're going to do is we're going to start with the bars, and I'm just working left to right. So we have x minus, and then if it moves to the left, what does that mean? That means h is equal to negative 2. And what I'm going to do, I'm going to put that negative 2 in for h. And notice how I did in the parentheses, much like how we did when we were doing our systems. And close the absolute value bar. It didn't move up and down, so k is 0, and I'm not going to write 0 in. What helps is if you write out your a, h, and k. All right, so a was 1, no dilation. H was negative 2 because it went left 2. And k was 0 because there was no up and down movement, so we didn't need it. Now, if you recall from those assignments from the first absolute value stuff we did, that when we're moving inside the absolute value bars, they were going the opposite direction. And why was that? Well, because of this negative from the formula. That negative is what makes everything turn opposite. So what do we know with a negative times a negative? It becomes a positive. And that's why it appears to be opposite when we're looking at the equation and the function's moving the opposite way we would think it was. It's not that it actually is. It is moving left. It is going negative 2. But when we apply it to the formula, negative times a negative makes a positive. So when we write the final result of the function, we get x plus 2, the absolute value of x plus 2. All right, and that's why it appears to be opposite, because of that little negative there. And this throws students off all the time. All right, so that is why it looks different. All right, let's go to the next example. All right, so this funny shape here is the cube function. All right, it kind of looks like a pinwheel to me. So we're just going to assume these go. If it goes to the graph, put some arrows on it. All right, this parent function starts at the origin, goes up like this, and then down like that. So it looks like it moved over to the right. So if you kind of just get the center, it moved 2 units to the right. All right, so cubic parent function, or you can write cube. All right, the effect, translate 2 units right. All right, and then the equation. So again, A, H, K. All right, so no up and down 0, no vertical stretch or compression, so just 1. And then your H, it moved 2 units to the right, so that means it's a positive 2. So when I write my function, so no reflection, none of that. So I'm going to start with X, and then the minus H, using our formula from next door. So minus, we're going to put H in there, which is a positive 2, and then it's cubed. No K value because it's a 0. All right, so negative times a positive 2 is just a negative 2, so we don't need those extra set of parentheses. So basically we get X minus 2 cubed, and again, you see how it's a negative, but this function moved to the right. Same idea, because of that negative in the formula, that negative made that positive into a negative. Therefore, it looks like it's going opposite. Okay, so H is actually 2, but in the function or in the equation itself, it's going to be an opposite sign. All right, so be very careful. So just to kind of reiterate that there is a plus here, and then when you combine these two together, we get a negative. All right, so I wanted to hit those two off because this is where students miss it all the time. We'll have whole exams where the student will get all the transformations right, but not the H ones, and it just totally throws them off. All right, so be very careful with that. Okay, they appear to be opposite from the finished equation, but if you dissect it, it only changed that way because of that negative from the transformation formula. So really, really, really beware of this negative here. It is there and it changes things. Okay, so let's look at this one here. Now we got equations. So f of x equals 2, those bars means absolute value of x. So what is the parent? Absolute value. For color, there we go. All right, what's the transformation? Well, it's a 2 in the front, so that's going to be a vertical stretch by a factor of 2. All right, it's vertical stretch. I'm writing VS for short. Here, they're nice enough. You're all welcome that we gave you the parent function. And basically what I'm going to do is, since to graph this correctly, I would have to make a bunch of x values, plug it in, and basically table it out and then plot a bunch of points. But since I know it's a vertical stretch, what it's going to do is it's going to pull this function vertically. And what I'm going to get is I'm going to get a much narrower absolute value symbol. All right. And that's how you would graph it. So I'm not expecting to table them out. We will table out functions like when we start them off, when we introduce each function. But for now, for the transformations, just show that they're more stretched out or more wider if it's a compression. All right, so there it is. So absolute value gives the equation. We wrote the transformation, and we did the graph. So next one, this is the square root function. All right, and it has a negative in front, which means it's reflected about the x-axis. All right, so there's the parent function there, and if it's reflected, it's basically going to go off this way. All right, and you can also put this in decimals, put the negative in there, and then you can see how it changes. Okay, so there it is. All right, on this one, we have the graph and the parent function again, but this time they're going to give us the descriptions, and we're going to write the equation. So vertical compression by a factor of 1/3. So if it's getting compressed vertically, it's going to squish it towards the x-axis. So this is basically going to widen out more this way and widen out more this way, like it's been squished. All right, and since it's quadratic, using my transformation function down here, we're going to have f of x equals it's a compression, so it's going to be 1/3. It wasn't reflected. X squared. All right, for quadratic. All right, so this tells us here, if we know parent function for quadratic is x squared. All right, now we have the square root translated down 3. So all I'm going to do is count 3 down, 1, 2, and 3. All right, and it goes off this way. All right, and then this is going to be f of x equals the square root of x. Now, since it moved down 3, you got to be very careful here to make sure we put plus 3 outside of the function. Excuse me, not plus 3, minus 3 outside the function. All right, if you put it inside the function, it's going to move right 3. Okay, so we have to make very clear that it's outside the parentheses. You can kind of imagine parentheses inside the little square root house or radicand that we call. All right, so again, square root function, y equals square root x. You recall, we try to get y'all to memorize those transformations. All right, so one last thing, I do want to write a couple of these parent functions or a few of these parent functions for you in the transformation form. So let's go ahead and start with linear, okay, good old algebra 1. Okay, f of x equals plus or minus ax plus k. We have absolute value. Absolute value x minus h, and we saw this one already, plus k. Then we have quadratic. And notice how they're very similar to the formulas up top, except I'm changing them with their parent derivatives. Okay, and do cubic. And square root. Notice how h is inside because it moves left and right, and then plus k outside. And then we'll do rational. Rational is our hardest one. Okay, I just wanted to do a few here, but since this is the hardest one, it's kind of weird because a is on top in the numerator over, and then basically what's on the bottom is the parentheses x minus h, and then plus k out here. Alrighty, guys, those are transformations and function notation.